Hi, it's Dr. Romeo Bruni, and today we're going to talk about chaos theory in the universe. This is a subject that I find very interesting, and I hope you will too. First of all, chaos theory. How was chaos theory first invented, if you will? The first probably was Edward Lorenz, who was trying to model weather. And he had this system of equations that modeled the weather. And he modeled the weather one day and found a particular storm that he really liked. The next day he said, let's model it again. So he took the same data, he thought, input it all, and rather than getting a storm, he got a beautiful day in his prediction. And he was going, what's going on here? When he backtracked and checked, he noticed that he had input the data only to 3 or 4 digits when originally it was to 8 digits. So even though this tiny change was so minute, it produced a few days later such an extreme change in the weather that he was shocked. And that was the original chaotic model. This is the Lorentz attractor. We'll explain this more in detail. So that there's 2 elements of chaos. The first is that they are highly unpredictable. Even though the equations or the system you're analyzing is both dynamic, which means that it's changing over time, and more importantly, it's deterministic, which means there's a definitive set of equations that accurately describe from one moment to the next what the system will do. So theoretically, if you have a dynamic deterministic system, you should be able to predict into the future. The problem and the difference between chaos theory and a simple deterministic system is this sensitive dependence on initial conditions. This is summarized and known as the butterfly effect. And what the butterfly effect is that even though the equations are deterministic, a very slight change in the input conditions can produce a very dramatic and profound change in the output conditions, i.e. the sensitive dependence on initial conditions. Lorenz described this as the brazilian effect. His exact quote was, the flapping of a butterfly's wings in Brazil can a few days later produce a storm in Texas, the so-called butterfly effect. The interesting thing here is even though the system is chaotic and the conditions are very dependent sensitively on the initial conditions, the output will depend. Overall, there are factors that lead to predictability. For example, that is not totally random and chaotic. You can see that the output actually has structure. So chaos theory has both unpredictable elements and highly structured, predictable elements. So how does that fit into the universe? Well, the universe is in essence a chaotic system. It's dynamic, it's deterministic. What happens in the future depends on the present. And it's very sensitive on the initial conditions. Now, since we can't measure the initial conditions to infinite precision, you'll always have some fluidity in the initial conditions, which means that your output cannot be totally predictable. So where is the chaos? Where are the deterministic principles that determine the universe? Well, the principal builder in the universe is accretion disk physics. And accretion disk physics has to do with matter swirling around a gravitational source. So when you have a combination of angular momentum, and gravity, plus gravity, gives you accretion disk physics. So let's examine where in the universe we get this type of deterministic system and what it produces. The simplest example is something like the solar system. The solar system is an accretion disk around the sun. We have the sun in the center, and all the planets are rotating around the sun, all in the same plane. That's why the planets come across in the ellipse, all on the same plane, because it gets flattened down to the same plane. When you have a bunch of stuff rotating around a central gravitational object, the stuff tends to merge to the equatorial plane of rotation and concentrate itself there. That's why all the planets on all the material in the solar system gets crunched down into the equatorial plane of the solar system, and you get the planets forming. All planetary systems are going to form like that, so they're going to form in the equatorial plane of rotation of the sun or this whatever star in whatever case. So we can see then, therefore, that every star can have a planetary system around it and form a solar system, if you will. Also, bigger stars, black holes, for example, they also form accretion disks. And that's why we see pictures of black holes. You always see the accretion disk that's flowing around the black hole. Again, it compresses down to the equatorial plane, all the matter, and starts to flow in an accretion disk. And in fact, the accretion disk around black holes is the only part of a black hole that's visible. A black hole, by definition, is black. Light cannot escape it. But material streaming into the black hole gets heated up as it starts to stream into the black hole and emits a humongous amount of light, which can be extremely bright. In fact, what we call a quasar is an accretion disk around a supermassive black hole. They can be and are the most powerful lights, most powerful constant energy stream in the universe. So we see that around every star, you can have accretion disks. They can form planetary systems, or they can form accretion disks that are visible. In fact, planets have accretion disks. For example, Saturn, the rings of Saturn. If that was Saturn, all the rings of Saturn are all due to accretion disk physics. The Saturn is rotating like that, all the material comes down to the equatorial plane, and you get the rings. So planets have accretion disks, stars have accretion disks, the solar system is an accretion disk, but the biggest accretion disk of all, and the most important element of this discussion, are spiral galaxies. Let's look at what happened at the Big Bang. In the Big Bang, you had all the material, all the matter, all the energy in the universe was created in a moment and then dispersed out, ever expanding. And the way it was sent out was like in droplets. And each droplet of material that was sent out eventually forms a galaxy. One droplet forms one galaxy. And in each droplet, we have, let's just do an expansion of one droplet. This is a big sphere now that contains material and energy. It contains only three things. It contains dark matter, hydrogen, and then helium, because a certain amount of hydrogen gets converted to helium in primordial nucleogenesis in the first 3 minutes of the universe. So after 3 minutes, you're left with only three things in these balls: dark matter, hydrogen, and helium. Of course, you have a lot of photons and that type of energy, but not important to this discussion. So DM, hydrogen, and helium. The deterministic system here is that each of these balls has these three things only. There is no central gravitational mass, but then does the accretion. Even though in each one of these balls, very early in the formation of the universe, you have a collapse of humongous dark matter clouds to form a supermassive black hole, which is millions to billions of solar masses in weight and is one at the center of every emerging spiral galaxy. Even though these are humongous, the amount of gravity or weight in a supermassive black hole is not sufficient to accrete a whole spiral galaxy. So where does the gravitational heft come from? It comes from the dark matter. Now, because dark matter interacts with itself and other things in the universe only through gravity, it's dark, it does not interact with electromagnetically or in any other way. When you have these huge spheres of dark matter, hydrogen and helium, and they're all in the sphere, the very important thing that they have in common, the unique thing they have in common, is that they're all coherently spinning. So you have this big ball of hydrogen, helium, and dark matter, and it's all chaotic at first, all spinning around. Because of this common coherent spin, and the fact that the dark matter does not bump into itself, and you need friction to get accretion. Because of friction, you get loss of angular momentum, and that causes everything to float or accumulate in the equatorial plane. Because dark matter does not interact with itself by bumping into itself or anything else, all it does is provide gravitational potential. So the dark matter continues to just spin around in this sphere-like state that it was in. But the hydrogen and the helium, on the other hand, with the dark matter providing the gravity well, because the dark matter is all in here like this, but the spinning dark matter provides a gravity well which appears as though it's concentrated at the center. And it's the spinning dark matter cloud that causes hydrogen and helium to compress down to a disk, and the equatorial plane of the spinning dark matter halo. And this disk, this hydrogen and helium come down and into this disk where stars start to form. And these stars start to form in this disk, and they are also continuing to spin just as they did originally, and just as the dark matter continues to spin. But now it's been compressed down into this disk shape. And this disk shape then further defines itself into spiral galaxies. Therefore, the initial and primary galaxy type in the universe are spiral galaxies, period. If left to themselves, the universe would have spiral galaxies and only spiral galaxies. But what happens is that even though you get these spiral galaxies forming in each of these droplets, if these droplets or galaxies start to interact with other galaxies, that's when you get the other types. Because if you have two spheres coherently spinning that come together, unless they come together at exactly the perfect angle so that their angular momentums cohere and add to each other and maintain, in which case you get a massive spiral galaxy. More likely than not, they're going to come in at different angles to each other. And when they come in and they sort of pass through each other, and then they come back and pass through each other again, you get total loss of this coherent spin that was there in the dark matter. So you get loss of all this beautiful definition that you see with spiral galaxies, and you get the other type of galaxies. When two spiral galaxies merge, you get an elliptical galaxy. So elliptical galaxies are just merged spiral galaxies, and they will be bigger than spiral galaxies, and they will be these big blobs of stars in a sort of a spherical shape with no beautiful, intricate spiral shapes. So what controls what the spiral galaxy is going to look like. Well, there's only really three things, and that's the size of the ball, i.e. how much dark matter, hydrogen, and helium are in these balls. You get some are small and some are big. And then what is the rotation rate of the dark matter, hydrogen, and helium? Some of these little balls are going to be rotating faster than others. And then what is the proportion of the dark matter versus hydrogen and helium in each of those balls? In some galaxies, they may form with very little dark matter, in which case you don't have this coherent push towards a spiral galaxy. In that case, you may get a dwarf galaxy that does not have the beautiful delineation of a spiral galaxy. In order to get a spiral galaxy, you need a large amount of dark matter that's coherently spinning. So, in fact, so every spiral galaxy in the sky is really a strange attractor. Strange attractors are fractals. Strange attractors are, that's an example of a strange attractor, meaning that because of the dependence on initial conditions, you can't really predict where you're going to end up in this a strange attractor, yet it shows that it isn't completely random and isn't completely stochastic what happens. In fact, there's a predictability to the chaos. And in case of the universe, the predictability is that you are going to get solar systems because of accretion disk physics. You're going to get accretion disks around every star, around every black hole. And of course, you're going to get accretion disk physics creating spiral galaxies out of all these little blobs of hydrogen, helium, and dark matter that were sent out. Of course, all galaxies popped out of the Big Bang at the same time and then started to form. And it took, after they pop out, there's no stars yet, so you enter the dark ages. Very early in this spherical ball, you get dark matter clouds forming a supermassive black hole at the center. The supermassive black hole at the center starts to polarize all the galaxy within its reach. And then the hydrogen and the helium start to come down into a disk, and they start to form stars. And the stars light up, obviously, which then ends the dark ages. So the first thing you're going to see when we look back with the James Webb Telescope is early disk galaxies. They're going to be highly formed at a very early age, 400 million years after the Big Bang. You're already going to have perfect disk galaxies starting to form. This theory meshes perfectly with the James Webb data, which has shown that you have very early and very organized disk galaxies much earlier than they had anticipated, but not in my estimation because of this chaotic system where you have a dynamic deterministic system. The deterministic system is accretion disk physics. Every spiral galaxy is in fact a type of strange attractor, because every galaxy is going to have slightly different amounts of hydrogen, helium, and dark matter. In other words, you can vary the initial conditions in one of three ways: the size, the proportion of these three things, and the rotation rate. When any of those three conditions are varied, you're going to get a different spiral galaxy resulting. Since no two spiral galaxies are ever going to have the same three initial conditions exactly, thus no spiral galaxy will ever look exactly like another spiral galaxy. They will be similar, just like snowflakes can all look the same. One snowflake kind of looks like every other snowflake, yet there are no two snowflakes that are ever exactly alike for the same reason, because even though the system is deterministic, you cannot predict every single outcome because you cannot get the initial conditions down perfectly. So the universe is in fact an example of a chaotic system because it's dynamic, it's deterministic. The deterministic system is accretion-based physics, and it has sensitive dependence on the initial conditions, which tells us that spiral galaxies will all kind of look the same, yet all be different. Chaos in the universe. Hope you enjoyed this. Ciao.